Everybody, I'm going to go over intermolecular forces in this video. So these are just the attractive forces between individual molecules. You might see it abbreviated as IMF. This should be fairly reviewish, so I'm going to go through it a little bit quickly. If you want to read through more in depth, it is section 1.13 in the textbook. So intermolecular forces, they do affect things like solubility, melting point, boiling point. So they have a lot of impact on physical properties. Solubility is just like, if you have intermolecular forces that tie two different molecules together, they're going to tend to be more soluble together as well. If we've got the more intermolecular forces we have, typically the higher your melting point's going to be, higher your boiling point's going to be, because basically what's happening is you're just kind of stitching those molecules together strongly. And the more strongly you do that, the more they resist going into that phase change motion there. So I'm just going to go through the three main intermolecular forces. So that's dipole-dipole, hydrogen bonding, and fleeting dipole-dipole interactions. So for dipole-dipole interactions, I'm just going to kind of show this in terms of like melting point, boiling point comparisons between molecules that have such and such interaction and molecules that don't. So in this case, we've got formaldehyde. It's got a melting point of -92 and a boiling point of -19. It is a very small molecule, so that's not very surprising that we have that low of melting point, boiling point. On the other hand, if we look at ethylene, which is the 2-carbon double bond molecule, the melting point is -169 and the boiling point is -103. So if you just compare these two, this is significantly lower in terms of melting point and boiling point. And the reason for that is those dipole-dipole interactions. So obviously you can't have a dipole-dipole if you don't have a dipole to start with. So the way that you get a dipole is you've got two different elements that are of differing electronegativities forming a bond together. Okay, so an oxygen is going to be more electronegative than a carbon is. So I'm going to use the same kind of delta plus, delta minus notation that we used in our induction video. So if you can see induction, you can generally see dipoles, okay? Because this is our dipole. We kind of draw them as like arrows pointing towards electronegativity. So in this case, the oxygen is gathering up most of that electron density and stealing it away from the carbon. So it's an uneven share of electron density between the oxygen and the carbon. So the reason that this can be used to kind of keep molecules together is if you imagine that we have a whole pot of this formaldehyde or a whole flask or whatever you decide to make, and we've got a delta minus over here and a delta plus here, those can line up and then have this plus minus interaction at the carbon and the oxygen. So this is your dipole-dipole interaction. Okay, so these two things are getting kind of pushed together or pulled together because of that plus minus pairing. On the other hand, over here, we don't have any dipoles. These are all just covalent bonds. There's no polar covalent bonds present. So we can't have any kind of dipole-dipole interactions here. Oops, all covalent bonds. Okay, so we don't have any of those dipole-dipole interactions. So that's kind of the basics of dipole-dipole. You have to just identify a dipole by different electronegativities, and then those are going to line up to match each other. There are really nice kind of electron density map pictures in the book if you're interested in looking at those. Okay, so for hydrogen bonding, there's a couple of things that we need to have in order to do hydrogen bonding. You have to have an atom with a lone pair on it, and you have to have an H that is attached with a polar covalent bond to some atom. Okay, so if we're looking at some options here, these two, H and N are polar covalent, H and O are polar covalent. So these are good H bond donors. Okay, and the H bonding comes in kind of two different flavors of the two different parts. So whatever is providing the H is called the donor. Whatever is taking the H, not really taking, but sharing the H is the acceptor, okay? So if I'm looking at something like this, that is just a covalent bond. Oops. So this cannot do H bonding. Okay, so we're really needing to be careful here. It's not just any kind of like CH bond that can do hydrogen bonding. You're generally going to be looking for NH, OH. Those are the more common ones. And then you have a couple of other things like, I'm trying to keep it with drawing my atoms out for now. So then you can have stuff like this oxygen can be used as your H bond acceptor. Okay, I'm not terribly worried about you being able to identify donors versus acceptors. I just want you to show, I just want to show you that you can do things even if there's no H on this molecule that can be used as an H bonder. This can still participate in hydrogen bonding with like water or something like that. Okay, so let's take a look at these molecules. So this molecule right here is called trimethylamine. Meth means one, and these are all methyl groups. And then this is an amine altogether. So that's how that name comes. So this one has a boiling point of 3.5. But if we take one of these methyl groups and just kind of put it over here, so that's what this, this is an ethyl methylamine. Eth is 2, so that's the 2 carbon piece over here. Meth is the 1 over here. So this now has this NH bond attached to it, okay? So if we go ahead and imagine, again, a whole flask of this amine, then I can just be having another of those amines over here. Takes me a bit to draw it all out. This is why we have the skeletal structures and the shorthand and stuff, because otherwise, and it's an eternity long. I'm exaggerating there a bit, but you guys know what I mean. Okay, so then we can have a hydrogen bond right here, where we're essentially having, again, that pull, that attraction, because we've got a delta minus here, delta plus here, delta minus there. So again, this is actually a type of dipole-dipole interaction because we're using the fact that this is a dipole, this is a dipole, and we're actually able to kind of share that H that's positively charged between those two delta negative nitrogens, okay? So I just wanted to show very briefly that you can do this with 2 different molecules. So this is acetone, this is water. So obviously the water here, it could do hydrogen bonding with just itself in a way very similar to what we have up here. And then the acetone doesn't have any hydrogens that are actually able to do hydrogen bonding because these are all covalent bonds, but we can do hydrogen bonding between the oxygen of the acetone and the hydrogen of the water so that we have our hydrogen bond right here. Okay, so that bond that I've just drawn there is the reason why water is soluble in acetone, okay? Because we have quite a strong hydrogen bond, intermolecular force, allowing us to make those 2 things soluble and kind of merge together, okay? So then our last intermolecular force that we're going to talk about is the fleeting dipole-dipole interactions. And I just realized I meant to get a picture in here. I'm going to pause real quick and add that in. All right, I got the picture in that I wanted. So I just stole this from the textbook. So this is a picture of the London dispersion forces. So you might have heard them called London dispersion forces in Gen Chem. You might have heard fleeting dipole-dipole interactions. They are called a couple different names. I think fleeting dipole-dipole is a better description of what they are. Like London dispersion doesn't really tell you that much. But if you look at these two hydrocarbons here, so this one is butane, this is pentane, pent being 5, but being 4. So we have a boiling point of 0 degrees for the butane, and then pentane has 36 degrees for boiling point. So you can see that just with the addition of one carbon, we have actually quite a significant change in the boiling point in that physical property. So the reason for that comes down to these kinds of interactions where every molecule kind of has like a center of charge. And most of the time, statistically, in something that doesn't have any dipoles, it's going to be in the center, right? But there's going to be fleeting moments where that center of charge might be over here, or it might be over here. And if you get two of those fleeting dipoles to line up together, then you can have a negative and a positive interaction, just like we've been seeing. So at the end of the day, intermolecular forces are all just about identifying where you can have delta plus, delta minus, and those two things are going to combine, okay? So the important things to know about London dispersion forces, everything has these, right? Everything has the potential for these fleeting dipole-dipole interactions. The more surface area you have, the more interactions that you're going to get. So larger molecules are going to have higher boiling points because they have more of these fleeting dipole-dipole moments, okay? So that's going to be a really big factor for large molecules. You'll see that even stuff that has hydrogen bonding, if they're larger, they're also going to have the impact of this as well. But if you're just talking about hydrocarbons, this is the only intermolecular force that they have because they don't have any real dipoles, which is required for the other two options. So just to wrap this up quickly, there's some really cool things about intermolecular forces. So these forces are actually what allows geckos to walk on walls because they have such a huge surface area on their feet. Then they have really big dipole-dipole interactions in that fleeting term. So they can actually walk on stuff and stick to things using those intermolecular forces. Hydrogen bonding, you're probably pretty familiar with because that's what gives us the DNA in our alpha helix, that shape. It is made that shape because of hydrogen bonding, specifically stuff like this kind of thing where you've got some sort of carbonyl with some sort of OH or NH bond, okay? So your book does a really good job of kind of showing the really neat things, and they even have a little box about the gecko feet. So definitely give those a look and start looking through maybe some of your old Gen Chem stuff for review. So anyways, let me know if you have any questions and I'll see y'all later.